Today a new topic, but part of the theoretical part of the course. Remember the previous topic that we studied so far was focused on information theoretic secrecy, and the whole target of that part was the last part of it, which is basically being able to calculate secure rate of transmission, and that secure rate of transmission is used as a theoretical measure of how good the security of your system is. So the higher that rate, the better the security of your system, and the lower that rate, the less security you have. And if it goes to zero, then this system is not capable of secure transmission. So that's what we did so far. Now we move to still some theoretical part, but this is the part that we will study today and in the coming couple of lectures, is the fundamental of how encryption is being performed. Remember that in order to secure your communication, the most practical technique available nowadays is using encryption. So you change the data somehow in a way that makes it not possible to retrieve the original data without having something called the key. And that whole process is called the encryption or the cryptography, the whole science or the whole process, okay? So where does this come from? What we will study in the number theory, which is what we will look at today and in the coming couple of lectures, is the fundamental mathematical background that tells you how security works. The whole idea of number theory itself as a branch of mathematics is discussing how to deal with integer-only operations. So operations that you perform on integers, and the results are always integers, even if you do division, right? So remember, when you studied your primary school math, you can add two integers together to get an integer, multiply two integers together, you get an integer, but the problem was when you divide an integer by the other, sometimes you get an integer, sometimes you get something else. You get a fraction or even a decimal number, right? So when we deal with number theory, we are dealing with operations that the input to these operations is integers, the output are also integers. Not only that, there is one more restriction. We are typically dealing with something called modulo arithmetic, or sometimes they call it modular arithmetic. Sometimes they call it finite field arithmetics. In the regular arithmetics, even if you are dealing with integers, your integer number can take a value from 0 on the positive side, from 0 all the way to infinity. 9, 10, 100, 1000, whatever. Similarly, on the negative side, it can take any value from either 0 or -1, all the way to minus infinity, right? In number theory, no. We are dealing with a finite field, so the values of our integer are up to a certain maximum value, which is the field size -1, okay? And then if it goes beyond that, it just loops and comes back. So the integers that we'll deal with, for example, will have values from 0 to 11, from 0 to 19, from 0 to 3, from 0 to 10, whatever, okay? That's called modular arithmetic. So two things, we are dealing with integers, and we are dealing with those integers within something called the finite field, and that operation or that part of operations is called modulo arithmetic or modular arithmetics, okay? So let's start. This should be, this is number 5, right? Lecture set number 5, not number 3. I will correct this, okay? Okay, so we start with trivial concepts, but they are essential to keep them in mind, and then we will build on them as we go further into the topic, okay? It's a very fun topic, by the way, so very interesting. I usually find students intrigued by this topic, okay? First thing is we define something called divisibility. I think you studied this maybe in your grade 4 mathematics. Yeah, so grade 4 primary school, okay? We say that a number, okay, B divides A, right? If we can write A, right? If we can write A as integer multiplied by B. So we say that B divides A if we can write A equals some integer multiplied by B, right? So we say, for example, 2 divides 8 because we can write 8 as 4 times 2. The 4 is this part, and the 2 is this, okay? And the way we write this formally in number theory, that's something probably you did not address in your grade 4 arithmetics, is we say B, and this sign means divides A. So B divides A, okay? This means that you can write A as some multiples or integer multiples of B. Okay? Don't forget that even A and B here are integers. They can be positive or negative, by the way, okay? Okay, and again, if B divides A, then we call B a divisor of A, right? That's also some basic. I don't think we need to take examples on those, right? So I will skip the examples. Let's go to the next step. If a number A divides the number 1, then the only possible values for A are plus or minus 1, right? No other possibilities. No other number, integer number, will divide A, okay? And the other thing is, if A divides B and also B divides A, so if A is a divisor of B and B is a divisor of A, then the only possibility here is that the magnitudes of A and B are equal, right? So A is equal to B or A is equal to minus B. They have the same magnitude. Any number B which is not equal to 0 is a divisor of 0. So any number B divides 0. Why this is the case? Because 0 times anything is equal to 0. So all the integer numbers are divisors of 0 except 0. Okay? Now the other thing is, if A divides B and then B divides C, then the consequence is that A is also a divisor of C. Right? Imagine of this as like the small guy, this is a little bit bigger, and then the biggest guy, right? So if I am a divisor of a smaller guy, right, and that smaller guy is a divisor of a bigger guy, then the smallest is a divisor of the biggest, okay? Another important property, and we will use this a lot in the coming few slides, if B divides some integer G, and also B divides another integer H, then if I combine G and H with any linear combination, so for any values of N and M, okay, the resultant is gonna be a number which B divides as well. Okay, is this clear? So if A divides G, B divides G, and B also divides H, then B is a divisor of some integer multiplied by G plus some integer multiplied by H for any N and M. N and M can take any value, okay? This is a very important property. Any questions so far? Toys, huh? This slide is just meant to show you why what we mentioned in the previous slide is true, okay? And the way this is shown, and that's one way of proving many things of those properties that we discussed and we will discuss in the coming few slides. It shows you how to actually prove or show that the relation that we mentioned in the previous slide is correct, right? So it says that if B divides G, then G can be written as, right, B multiplied by some integer, right? Because B is a divisor of G. So I can write G as B multiplied by some integer. And also if B is a divisor of H, then I can write H as B multiplied by some other integer, H1, okay? Now, if I want to combine those two, Mg plus Nh, that's the linear combination of G and H that we saw in the relation in the previous slide, then simply remove G from here, replace it by Bg1, and remove H, replace it by Bh1. The result is gonna be Mbg1 plus Nbh1. I can take B as a common factor outside, right? And this resulting number definitely is divisible by B because B is a common factor out of it, right? So this shows you that if B divides G and it divides H, then it divides Mg plus Nh for any M and N, okay? Now we start a little bit on the serious stuff, okay? So given any positive integer n, this slide is just the definition of the division operation that you also studied in your, maybe grade 5, not grade 4. So grade 5 during your primary school, right? So if A is a non-negative, given any positive integer n and any non-negative integer a, okay, so positive here means it's definitely not equal to 0. It's 1 or above. Non-negative means it can be 0 or any positive value, okay? If we divide a by n, right, so the division of a by n results in this expression. The division of a by n in the integer domain results in a quotient, right, some multiples multiplied by n plus a remaining part that cannot be represented as multiples of n. We call this the remainder. So any division operation has the quotient, the result of the division, integer division operation, and a remainder, right? And remember that the remainder is always less than the number that you divide by. Because if it was greater, then this means you can add one more multiple here, and then the remainder is whatever gonna remain after that, right? So always the remainder is less than the number that you divide over, okay? And how do you get the quotient? This simply by doing this operation. Again, this operation will might result in some decimal, right, or floating point number, but then you take the floor of that. So the integer part only of that gives you the q, and then the remaining, after multiplying q by n and subtracting them from a, the remaining part is going to be what you call the remainder, r, okay? I don't think, again, there is something really difficult about this. If there is, just please ask the question. And this is just a representation of this operation that we have been discussing in the previous slide on the number line. So the result of dividing a over n is a q multiplied by n, quotient q, and then between qn and q plus 1n, we find a value called the remainder inside here, okay? So that's the multiples here gives you the quotient q, and whatever you add after that until you reach the value of a is what's called the remainder, and it has to be in this range. It cannot be outside, otherwise this means that you have a remainder greater than n, and then you can take one more n multiple and make the remainder after, right? So the remainder is always somewhere between those two, okay? Any questions? Let's start now on a little bit more serious stuff, okay? You remember something, probably this one was like maybe grade 7, grade 8, right? So during your mid school or إعدادي يعني هنا, تمام? You studied something called the greatest common divisor, تمام? القاسم المشترك الأكبر. So the greatest common divisor. And it's typically, it's a divisor of two numbers, A and B, such that it is the largest. There is no other common divisor of A and B which can be larger than this. So this is the largest possible divisor of two numbers, A and B. We call that the greatest common divisor. Remember how you used to deduce that? Yeah. So you used to do what? Factorize the number into its prime factors, the other one, and then take the common ones, multiply those from one side, of course. Multiply those common ones, and the multiplication of those is going to give you the greatest common divisor, okay? That's how you used to deduce it, okay? Now, the problem is, okay, factorization, and that's one thing that we will see here in number theory. Factorization of any number to its prime values is what they call an exponentially growing operation. So if your number grows a little bit larger, the process of factorization becomes much more complicated, takes much more time and much more number of computations. And if the number gets larger, rather than increasing with the size of the number linearly, it increases exponentially, right? So a small growth after a while causes a lot of extra calculations, okay? So the calculation of the greatest common divisor using that methodology, the method of factorization only, becomes a very complicated process if you deal with large numbers. Imagine I give you a couple of like 6-digit numbers, and I tell you find the greatest common divisor, and then you set with each one of them. By the way, 6 is not really big, but for manual calculation, it is big, okay? And then you set with a 6 figures number, trying to analyze it into its prime factors, and the other one is another 6 figures number, and you try to analyze it into its prime factors in order to find the greatest common divisor between them. It's gonna take a very long time. While as we said, if you make the numbers smaller, then the factorization process becomes much easier, okay? Based on that, there is a method, and very old method. It was designed by Euclid. Euclid is Euclides, the guy who started the geometry from the Greek civilization. He came up with an algorithm that reduces these numbers to something smaller that you can factorize in an easier way. And that's what we will look at right now. But before we do that, let's look at the formal definition of the greatest common divisor, okay? The greatest common divisor of any two numbers, A and B, as I just mentioned, it is the largest integer that divides both of them, both A and B, right? If you want to write that in formal mathematics, you write it this way. So you say that the greatest common divisor of A and B, okay, is some integer k, not any some integer, but the maximum possible integer k that achieves, it is a divisor of A, and it is also a divisor of B, right? Everyone can read this and understand what it means mathematically? Tamam, okay? Now, it was found that, based on this definition, that greatest common divisor is gonna have two important properties, okay? One of them is kind of like easy to figure out, okay? The greatest common divisor of any two numbers is a divisor of both numbers, right? Because it is a divisor, even though it's the greatest, but it divides both of them. That's one. The other one is a little bit more complicated and not easy to find out. And I want you to try to figure out why this property exists, okay? The book itself doesn't provide a proof for this, but you can look it up outside the book, okay? If C is the greatest common divisor of A and B, then any other common divisor of A and B is also a divisor of C. Tamam? Again, if C is equal to the greatest common divisor of A and B, so it's the greatest common divisor of the two numbers A and B, then for any Z which is common divisor but not the greatest of A and B, okay, Z will divide C. Any other, of course, in this case, smaller divisor, right? Because C is the greatest, so it's the largest common divisor of A and B. Any other smaller common divisor of A and B will be also a divisor of C. Why? You cannot prove easily that it is a multiple.
Because if you factorize C, you will get to Z.
If you factorize
C, you will get to Z, which is small factor.
Why?
Because C is a multiple of Z.
Why? Can you prove this?
ممكن بالأرقام.
Arqam is not a proof. If you try example numbers, that's not a proof. You can verify, you can test it once or twice. But proof means write this with a mathematical logical proof that has like basic axioms behind it, and you didn't really just assume anything. You just went through. That's how mathematical proof is done, right? Can you prove it? That's the question. Okay, try. If you can prove it, that would be nice. Even today, if you want to try. If you can manage to prove it and show it to us, it's provable. I'm not saying it's impossible. It's provable. But the proof is not easy to catch. And it's not long, by the way. But it's not very easy to catch. Okay? So two properties, as we said, greatest common divisor. Number one, it's a divisor of both numbers, of course, by the naming. And then the second is any other divisor of those two numbers, A and B, are going to be a divisor of the greatest common divisor. Of course, including itself. Any number is a divisor of itself, right? So that's why the statement says any divisor, it doesn't say any other divisor. Any divisor of A and B is a divisor of C, right? Okay. Now, this example is just meant to, not really to like figure out the number, but what's meant from this page is to tell you that when you are trying to get the greatest common divisor of two numbers, right, A and B, this is the same as A and minus B, the greatest common divisor for A and minus B, or minus A and B, or minus A minus B. In all these cases, we try always to get the greatest common divisor, by the way, to be a positive number, okay? And it doesn't matter if you have two positive numbers, one positive and one negative, which are those two cases, or both of them are negative numbers, as long as the magnitudes of the numbers are the same, the greatest common divisor for all of those is going to be the same. And accordingly, when we calculate the greatest common divisor of any two numbers, we look for the one that uses the positive values all the time. Okay? Okay. Another important property, or like deduction, the greatest common divisor of any number and 0 is equal to? Why? No proof here, just logic. Why? We agreed before that A must be a divisor of 0, right?
0 multiplied by A is
Exactly, equal to 0. So any integer A, for example, in this case A, is a divisor of 0. Any integer we agreed is a divisor of 0, right? Since the largest divisor of A is itself, and since this is still a divisor of 0, then this means that the greatest common divisor of any number and 0 is the number itself. Okay? Okay. Another thing is, that's just a definition. If two numbers A and B do not have any greatest common divisor except 1, of course we know that 1 divides any number, right? So 1 is a divisor of anything, okay? Of any integer, okay? So greatest common divisor of two numbers A and B, if that greatest common divisor is 1, so those two numbers do not have anything common between them except 1, which is common between all the numbers, then we call those two numbers relatively prime. There is no common factor between them. And we call them in number theory relatively prime numbers. You cannot find any common divisor between them.
so 11 and 5 can be an example. Yeah?
Exactly. 11 and 5, 13 and 11, 13 and 3, right? Any prime number and any other number, right? Any prime number and any other, not any other number, any other number that does not include the prime number. Because any other number might be the prime multiplied by 3,
Example,
right?
11 and 8.
Sorry?
Example 11 and 8.
11 and 8, that's relatively prime. 15 and 9, 15 and 8, that's relatively prime. تمام? So any two numbers where the greatest common divisor of them is equal to 1 only, there's no other possibility, are called relatively prime numbers. Why these are important, we will come to them later. They will show up later as an important property. Okay, okay, what does the Euclidean algorithm do? This slide is not easy to understand. It's from the book, actually. I will describe it to you in a couple of steps, and then we will look at a flow chart that shows how it works, and then we will look at a numeric example to see or to better understand how it works. Okay? The Euclidean algorithm for finding the greatest common divisor is based on, as I said, if you are trying to find the greatest common divisor of two numbers A and B, the target of the Euclidean algorithm is to try to reduce the magnitudes of those numbers as much as possible. I will tell you what I mean by that, okay? Until it's easy to figure out their prime factors, because they become smaller numbers. And then once they become smaller numbers, you can actually find their greatest common divisor. Not only that, in fact, the end of the process itself gives you directly the greatest common divisor. Okay? And we'll see how it works. Okay, let's start. The algorithm itself is based on a very important property, that if you are looking for the greatest common divisor of two numbers A and B, okay? And here we always assume that A is a bigger number. Okay, so we always assume that A is greater than B.
Can be the opposite though.
If it's the opposite, flip them. Right? If you are looking for the greatest common divisor of 10 and 2, that's the same as greatest common divisor of 2 and 10. So you can always arrange them without loss of generality, such that the first one is the larger, the second one is the smaller. It doesn't matter to the result, right? Okay. So under the assumption that A is always B is greater than B is always greater than B, and if not, as I said, flip first and then start executing the algorithm. So now, assuming that A is greater than B, and you are trying to find the greatest common divisor of A and B, right? Now, let's try to represent A in terms of B, which means let's try to apply the division algorithm of A divided by B, right? If I try to divide A over B, what should I get? Some quotient, right? Multiplied by B, so some multiples of B, and probably plus some remainder, right? If I try to divide A over B, the result of that division, based on the division algorithm that we looked at a few slides ago, is gonna be some multiples of B plus some remainder value, right? And this is the quotient of the division. This is the remainder of the division. Tamam? Okay, so far nice. Okay. Interestingly, Euclid says, and that's easy to prove, by the way, and we'll try to prove it now, okay, that the greatest common divisor of A and B, okay, is also the greatest common divisor of B and that remainder R. So this guy is equal to this guy. So we started with two numbers. A is the larger, B is smaller. We are trying to find the greatest common divisor of those two numbers. And then we think they are big. So what we can do is represent A as, using the division algorithm, as a function of B, right? The result is going to be that the division of A over B will give you some quotient. We don't really care that much about the quotient, but we figure out a remainder of dividing A over B, okay? Now, instead of finding the greatest common divisor of A and B, this can be found by finding the greatest common divisor of this B and this remainder of dividing A over B.
The greatest common divisor between A and R.
لا ما حدش جاب سيرة A and R دلوقتي. So the steps is you start with A and B, greatest common divisor you are trying to find. Next step, you can reduce this by finding the greatest common divisor of B and R. Why this is a reduction? Because we know from start that B is smaller than A, right? And we know from the definition of remainder that R is always smaller than B. صح? The remainder of dividing by B is always a number smaller than B. تمام? So now we are dealing with two numbers that are smaller than those two. The left side is smaller than the left side, the right side is smaller than the right side. Keep repeating the operation. Now you want to find the greatest common divisor of B and R. Right? Again, write B, right? Using the division algorithm as a function of R. So it's some new Q, call it Q1, R, plus some new remainder, call it R1. Right? And then from the Euclidean algorithm, this greatest common divisor is also equal to the GCD of R and the new R1. And keep doing this until your remainder is equal to 0. When your remainder is equal to 0, right, the number that you have in the place of B is your greatest common divisor. So the process ends with the greatest common divisor right in front of you.
Doctor, when it will be 0? When it will be 0? I mean, if you keep doing this, it will be R1, then R2, then R2.
It will reach 0. It will always, it's guaranteed to reach 0.
How you can guarantee?
At some point, yeah, it's guaranteed. Don't worry. Because as soon as you get rid of the greatest common divisor of those two numbers, the result of that operation is going to be 0. You will see it. Okay? Don't worry. Okay. You want to see this written as an algorithm? First of all, any questions here? Of course, you might not have clarity how it gets executed. It will become clearer when we look at a numeric execution of this. But any like general unclarity about how the process works? Okay, one question for you. Prove to me that, try to think of this together. Prove that, okay, the greatest common divisor of A and B is equal to the greatest common divisor of B and R, where, okay, A is equal to Q, B plus R. So R is the remainder of dividing A over B. Can you prove this? And the proof is like 3 lines, right? And it relies on a property that we discussed a few slides ago about the divisor. Remember the divisor properties?
The A and B and
Yes, but use it. Yeah, but use it. Yes. Go ahead. You can talk together, by the way. This is not an exam. So you can discuss together how to drive this. So call this greatest common divisor something like C, مثلا. Okay. حد قرب من انه يجيب البروف؟ حد وصل لأي حاجة؟ طب نشجعكم؟ طيب I will wait for 2 minutes. Okay. If we want to show this, if C is a divisor of A and B, which is very similar to what you are talking about. احنا هنتكلم now we are talking about the greatest common divisor C. We know that C is a divisor of A و C is a divisor of B. صح؟ لأنها هي the greatest بس هي divisor لكل واحد منهم. تمام؟ This means what? That C is a divisor of any linear combination of A and B. صح؟ يبقى لما اكتب كده C is a divisor, is a divisor of A minus QB. الكلام ده صح ولا لا؟ C is a divisor of A, C is a divisor of B. This is a linear combination of A and B, so C is a divisor of this. صح؟ و this is what? This is R. صح؟ هقولها تاني حاضر. But this is R. Clear؟ اهو. مش دي relation between A و B و R? So this is simply R. So C is a divisor of R. صح؟ ما خلاص فاضل لك بعد كده تقولي هو ليه greatest بس دي ستيب 1 ستيب. طب كنت وريتيني طيب. كنت هديكوا تلتين البونص سيريسلي. خلاص؟ طيب نشرحها تاني. انا عشان عايز دول عشان عايز اجيبهم لهنا. ما هي C is a divisor of any linear combination of A و B صح؟ انا اخترت اللينير كومبينيشن دي ان الرقم ده يكون 1 والرقم ده يكون الماينس كيو. That's it. Why I selected those? Because I know that this will give me R here. تمام؟ So now I know that C is a divisor of R. فاضل one thing. Why it's the greatest common divisor. أنا عارف I know that C is a divisor of B. و now I know that it is a divisor of R, so it's a common divisor of B and R. Is it the greatest ولا لا؟ لا it is the greatest. ليه؟ Why?
لأن الآر أصغر فاكتور.
Yeah. So R is smaller than B. And I know that C is the greatest divisor of B. تمام؟ I will not find another divisor coming from R common with B that will be greater than C. الحتة الأخرانية.
مو بالكلام الكتابة هفهم.
طيب ماشي. Up to here you are okay? تمام. We know that C is the greatest divisor, okay, common between A و B. تمام؟ Agreed. Okay. Now I know that R is smaller than B. تمام؟ I know that C is a common divisor.
فالآر أكيد حتكون أصغر من C.
Yes. Common divisor between R و B. مظبوط؟ وبما ان C was the greatest divisor I was able to find for B, well R is smaller, then I will not be able through the R to find another bigger divisor. There is another way to write the last part ده in a more mathematical rigorous way by explaining if it is a divisor of this, then you can write it as multiples والتانية as multiples, and then you show that those multiples, one of them is not possible to be greater than the other, so this is the greatest common divisor. But or you can do it by logic مباشرة كده. Okay? Look it in the book, it's proven in the book. This proof exists in the book. خلاص؟ Okay? بس كويس انتوا يعني this is the Euclidean algorithm written as a flow chart. تمام؟ So you start the algorithm, you check the two numbers A and B that you want to get their greatest common divisor. If for some reason A is not greater than B, which is this condition, you swap. We agreed that we always want the first one to be the larger, the second one to be the smaller, so that the algorithm becomes consistent. If it's already true that A is greater than B, go to the next step, divide A by B, right, and then get the remainder. If the remainder is greater than 0, replace A with B. So we started with GCD of A, B, right? In this step, it becomes GCD of B, لأنه we replaced the A with B. And then replace the B with R, so we replace this with R, right? And that's the new GCD that we are looking for, the new greatest common divisor. Repeat the operation, so divide this by this, get the remainder. If the remainder is greater than 0, perform this again. Keep doing this until the remainder is equal to 0. Once the remainder is equal to 0, you exit the operation, and in that case, where the remainder is equal to 0, the number here, at that last step, the number on the right side is going to be your greatest common divisor على طول. Okay? Let's look at this in numbers. So now we did it again logical on a flow chart. Let's look at this being done in numbers. We start here by trying to find the GCD of the two numbers 710 and 310. تمام? First step, represent 710 as using the division algorithm as a function of the 310. So 710 is equal, this is our Q1 and this is our R1. تمام? So 710 is equal to 2 multiplied by 310 plus 90. Okay? Then the next step is going to be that this GCD is going to be the GCD of 310 and the 90. تمام? I take this and the remainder. Right? Now, next step, again, divide 310 over 90 using the division algorithm. You get this expression. Now I have this number and this number, right? So this guy comes here, 90, and the remainder here becomes the right side of this operation, GCD. Okay? One more step. Now I have 90 and 40. Represent the 90 as division over 40. So you get 40 and 10. So this is equal to GCD of 40 here, and the new remainder 10. If you divide 40 over 10, the remainder is equal to 0. Then this means that the greatest common divisor is this. 10. The right side of the last step, which results in 0 remainder. If you try now to represent 40 in terms of 10, you will get a remainder equal to 0. Then this is the last خلاص. You take this side, this is the greatest common divisor. تمام? Any questions? Any questions? It's clear. حد في حاجة مش واضحة محتاج اشرحها له؟ تمام.
ازاي ده ارقام بتاعت 2 multiplied 310 plus 9 division؟
اعملي ديفيجن بس بالكالكوليتور يا ستي. جاست 710 على 310.
ليش ناخذ الإجابة؟
عشان ما فيش هنا خلاص هنا there is no remainder anymore. ف this is the last step that had two factors ال 40 وال 10. هنا خلاص
يعني بيكون زيرو صح؟
ايه هو؟
اخر ستيب
اخر ستيب هنا remainder زيرو. فريميندر زيرو معناها there is no more representation, there is no more GCD لان GCD مع زيرو هتديك ايه؟ even imagine you do it, it will become GCD of 10 و0 which is what? 10. خلاص هي نفس النتيجة يعني. It's a useful step يعني. Okay. خلاص. The proof وبالمناسبة سؤالك لأن سؤالك ده إجابته مش سهلة. The proof that Euclidean algorithm works all the time, which means you will reach zero all the time, is a bit complicated proof. It's not something يعني we can just sit here and do it very quickly. Okay? This is a proof that the algorithm always converges or the algorithm always succeeds. And these proofs are not easy. In any algorithm to prove that the algorithm always works, that's not an easy thing to do. It's doable. And in many advanced, لو انت you are coming up with a new algorithm or anything, you have to show that it converges or it finishes successfully, guaranteed, right? And if it fails for certain reasons, you have to say that this algorithm works except in this situation and this situation. So you have to do it when you develop your own algorithm later on. But generally speaking, at our level now, proving that an algorithm always finishes successfully is not easy. Okay? Always finishes successfully, regardless of the two numbers. Even if they don't have a greatest common divisor, it will finish with 1, right? So at some point you reach 1. Okay. This example shows you really how valuable is the algorithm. So imagine that you are required to find the greatest common divisor of those two numbers. تمام? These are the two numbers that you need to figure their greatest common divisor, and imagine that you went to do it the way you used to do it in your primary education. So take each one of them, analyze it to its own prime factors, get the common factors, and then multiply them together so that you get the greatest common divisor. Analyzing this into prime factors is going to take really, really long time. Okay? And because they are larger number, you can actually get exposed to prime numbers that are not easy to figure them out. You know, typically we know the first maybe 20 very smart guys maybe memorize the first 50 prime numbers, but then after that finding a prime number is not something intuitive. You cannot just do it easily. You need a table or a list. Using computers and other algorithms, they were able to generate really much more of the prime numbers, but until today there is no generator that gives you all possible prime numbers. And there is always, by the way, there is I think it's in the range of hundreds of thousands of dollars if you can discover a new prime number. You need to write your own algorithm on the computer and keep it running probably for a few months. If your algorithm is really nice, if not, even if you keep it running for years, it will not be able to solve this, okay? So it's not an easy thing. Finding new prime numbers or larger prime numbers is not easy, okay? Anyways, okay, starting from next time, I will just give you a quick introduction of what we will do. We will start discussing the modulus arithmetic, okay? And just in terms of representation, okay, modular arithmetic, as I said, you deal with additions, multiplication, even division, subtraction within a domain of finite set of numbers, okay? We define that domain by something called the modulus. So we always say, for example, A modulus 3 or A modulus some number n, okay? This means what? First of all, this means the remainder of dividing A over n, okay? Now, if you divide A over n and you get the remainder can range from what to what? In this case, the minimum is 0 because we said the remainder is always positive, right?
Divide n over a?
Divide A over n. Modulus n means any number is divided by n, and what you write in your calculation is the remainder of that division. Okay? From 0 to
A.
n minus 1. It cannot reach n,
Yeah.
right? So this operation will give you some value from 0 up to n minus 1 only, right? So if you keep everything modulus, so you add two numbers, right? But you do this operation mod n. This means that whatever the result of the addition is going to be eventually mapped to that limited or that finite domain of numbers, because you will get the result of the addition and then you will divide it by n and get the remainder. So it's going to be some number from 0 to n minus 1, right? Multiply two numbers. You multiply them. If it's multiplication, mod n. You multiply them, and then the result is going to be divided by n, and you take the remainder. So the result of that multiplication, mod n, is going to be some number from 0 to n minus 1. So you stay always within this domain. Remember when you were doing your binary system, you studied digital or binary, right? When you add 1 plus 1, right? And you want to put the result in only one digit, what did you do?
One digit? What do you mean one digit?
You are not allowed to use two digits to represent 1 plus 1 in the binary.
Oh, we took it up.
Zero.
مفيش up هتوديها فين؟ So the result is gonna be 0. انت قلتيها 0. If I add if you add طيب لا بالمرة الثانية قلت 0. أنا يمكن سمعتها غلط. If you add 0 plus 0,
بس ده zero.
the result is 0. صح؟ If you add 0 plus 1,
It's one.
the result is 1. If you add 1 plus 0, the result is 1. If you add 1 plus 1, and you are still representing this with one digit only, 0, and we call this the XOR. صح؟
دكتور قلت zero.
طب شفت؟
ما سمعت. حفظ الحقوق.
Okay. احتفاظا بالحقوق. Okay. So what happened here is we want to represent everything within the same domain, اللي هو domain that allows only 0 or 1. It does not allow more digits. تمام؟ So we invented in this case, they call this the addition modulo 2, اللي هو XOR. XOR operation, صح؟ 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. تمام؟ This is actually addition modulo 2. Similarly, if we want to add any two numbers mod n, you add them and then you divide that by n and you get the remainder. Similarly here, when we add 1 plus 1, it gives us لا الأول 2, and then mod 2, this is gonna be 0, لأنه if you divide 2 by 2, the remainder is 0. تمام؟ فthat's how you represent something modulo n. خلاص؟ Okay. So again, two things to prepare us for the next lecture. أول حاجة, first thing is modulo n operation means we are limited in the domain. Number two, the meaning of modulo n is that everything is mapped into any number is mapped into the remainder after dividing by n. تمام؟ 100 mod 3 is gonna be what? صح؟
One?
صح. Why? Because the result of this is 33 times 3, that's 99, and the remainder is 1, right? So the remainder here is 1. Okay. Divide 100 over 3 and see what's the remainder. 100 over 3, it gives you 33, right? 33 will result in 99, so the remainder is 1.
بس هاي شلون مرتبطة بالحسبة؟ zero plus zero.
لا خلاص ده كده كنت بديكوا اكزامبل من الباينري دومين. Here I'm talking about mod 3. mod 3.
اوكي شلون ابي احط هاي بهاي شلون؟
طيب. Here all our operation are mod 2. ده اللي درستوه انتوا في الديجيتال. Okay? Was all your operation were mod 2. So 0 plus 0 is 0. 0 mod 2 is 0. صح؟ لأنه 0 divided by 2, the remainder is 0. يبقى 0 mod 2 is 0. تمام؟ 0 plus 1. تمام؟ The result of this addition before modding is 1. مظبوط؟ 1 mod 2 is 1 لأنه the result of the division is gonna be 0 والremainder 1. So it stays as 1. طيب 1 plus 1, the result is 2. صح؟ 2 mod 2 gives you 0. لا 2 mod 2 remainder is 0. بالظبط. you are mapping to the remainder not to the result of division. تمام؟ not to the quotient.
Basically means the remainder.
The remainder. The mod operation means take whatever number you get and represent it by the remainder of dividing over the modulus اللي هو ال n.
مثلا 11 divided by 7.
مش هنسميها divided بقى، هنقول 11 عشان نتعود. 11 mod 7.
لأنه أنا هاي فكرة المود من زمان عندي مشكلة فيها مع إنه عارفة إنها simple وسهلة.
تمام.
بس هو
11 mod 7 معناها the remainder of dividing 11 by 7 which is gonna be equal to 4. طب حد عارف where does this come from؟ y minus 11 mod 7 gives you 3. اشمعنى 3؟
ازاي فوق اصلا؟
هم؟
ازاي
If you divide 11 by 7 ايه remainder؟
زيرو؟
remainder.
الباقي
divide 11 by 7 الريميندر بتاع القسمة دي كام؟ 0 ليه؟
ليه فوق؟
11 by 7.
الريميندر بتاع القسمة 11 divided by 7 is equal to 1 والريميندر is equal to 4. صح؟ اوكي تمام. I know we have exceeded 315. Y minus 11 mod 7 gives you a remainder of 3. Remember we said we want the remainder always to be positive number. تمام؟ So خدوا بالكم من النوت الأخيرة, this last note, okay? When you are doing mod operation for positive number, يعني 11 mod 7, okay? The way you get the remainder is, of course, you initially figure out the quotient that gives you something, تمام? Smaller than 11. And the remaining part is gonna be the remainder R, اللي هو الأربعة. فin this case, the quotient is equal to 1. 1 times 7 gives you 7. That's smaller than 11. The difference is 4. That's the remainder. طيب, in this case, minus 11. If you want to divide it by 7, تمام? Someone might say that the result of the division is minus 1. But if the result of the division is minus 1, then when you multiply minus 1 by minus 7 gives you what? By 7 gives you what? Minus 7. Minus 7 is greater or minus 11 is greater? Minus 7. We are looking for something smaller. So we have to take it beyond minus 11. So the result in that case is going to be minus 2. Minus 2 times 7 gives you minus 14. How much you have to add to minus 14 to get to minus 11? 3. That's the remainder. This is the only way to make sure that the remainder is always positive, not negative. خلاص? So for negative numbers, you multiply by something that takes you into more negative, and then you take the difference as the remainder. Okay? شكرا.